They'll be coming up now.
I cannot see nothing.
Yeah, 20-ish.
Yes, let's
Well,
go
that'll be
on. then. Good morning, good afternoon, wherever you may be in terms of joining us for our Technion webinar. We will start in about 1 minute. It takes just a couple of minutes for Zoom to populate all the different attendees. We're expecting over 300, so just hold on, and thank you so much for joining us. And as many of you are joining us, we're proud to say that the director of R&D for Zoom is a graduate of the Technion and enabled the technology to be available to all Technion faculty, students, and staff. So there's definitely a Zoom Technion connection. And again, we'll start in a little less than a minute. I'm going to close my door here in Haifa or Seattle. Again, we'll start in about 20 or so seconds. We're just waiting for Zoom to populate. People from all over the US and frankly, all over the world today. And we are really thrilled that you're joining us. Okay, I think we can get started. So good morning, good afternoon, good evening, whatever time zone you may be in joining us today. Hello, I am David Chivo. I am the Chief Development Officer of the American Technion Society. And let me begin by thanking you all for joining us today. And for those of you who will be celebrating the start of Passover tomorrow night, I'm really moved that the story speaks of moving from a period of suffering and specifically of plagues to the creation of a community, one that's grounded in new ideas, and most importantly, in shaping a new future. And so it is my hope that for many of us, as we welcome Pesach, that we may be infused by that spirit around this holiday, and that the Pesach celebration will be meaningful to you and to your loved ones. So to everyone on the call, Hag Pesach Sameach, and you from the American Technion Society, you really have all of our very best. Your interest continues to make the live from Technion webinars a resounding success. We're really thrilled to see many of you who are repeat attendees, and welcome also new friends for whom this is the first time joining us for what is in fact our fourth program. And as I personally reflect on the last few webinars we've held, I'm really filled with an appreciation and admiration for the Technion. We can draw hope and optimism to know that the Technion today is truly on the front lines of combating COVID-19, whether it's in its labs or on the front lines in hospitals all over Israel. And today, we not only welcome American friends of the Technion, but people from all over the world. And in the past, and I believe for today's call, I think that includes people from Great Britain, from Brazil, Japan, Canada, China, France, and Italy. So we have a little bit of a United Nations, and we're united by what draws us together, and that is the amazing work of the Technion. Before we move on to our featured speaker today, I'm truly honored to have Dr. Yehuda Sabiner join us from the Sheba Medical Center, which is just outside of Tel Aviv. Dr. Sabiner is a Technion graduate and a medical doctor who's really been on the front lines of battling COVID-19. He's the first Israeli doctor raised and educated in a Hasidic community. Nearly 35 other members of the Haredi, ultra-Orthodox community in Israel, have since followed his lead and gone to medical school. Yehuda is able to join us for just a short while as he's about to go on duty at this very busy hospital. So we'll first hear from him and what it's been like to battle COVID-19 from inside one of Israel's busiest hospitals. So Yehuda, Toda rabah. Thank you so much for joining us and for taking time away from your busy days, probably nights, to join us. And I now very proudly turn the program over to you.
Thank you. So hello, everybody. I am thrilled to be in this forum. I have a lot of gratitude to the Technion. So when Irma asked me if I can join the webinar, I told her if I am not on duty, of course. So my name is Yehuda Sabiner. I'm a father of 3, and I am now currently in the first months. I started the second month in internship in the Tel HaShomer Sheba Hospital. Tel HaShomer Sheba Hospital is the biggest hospital in the Middle East. In normal days, we have 1,800 beds. Don't ask me how much we have today. It's probably much more. So I came in the first day of internship to the department where I was meant to start here the internship, and instead getting a welcome, and this is our crash, this is our CPR room, this is our terms of how we're dealing with. They told me, listen, you have 24 hours to tell us if you're coming with us to the Corona hospital or not. We understand it's scary, and it's in your hands to say yes or no. Those days, we didn't have any patients with Corona, confirmed with Corona. Only the people, the travelers that came from Prince Diamond ship in Japan that was in quarantine just, as a precaution. And of course, I was scared like everybody. And I made a phone call to my wife, and I told her, they asking me to say if I am coming inside or not. It's right now, it's pretty much, it's voluntary. It's not a must, but it's going to be nice. And she told me, if you came to this point and this is what they telling you to do, so this is what you have to do. And we said both that we are in. And 2 days after it, I came to the Corona department, and we started getting patients with confirmed COVID disease. In the beginning, it was surrealistic, because when you went out of the hospital, people was laughing. What is the tararam that you're doing around this illness? It's just a flu, and people was very not scared about what is coming and what seems to be later in the upcoming days. And during we are in the hospitals, we're getting, the politicians and the managers of the hospital, and I see how much money they putting, and they just preparing to the bad situation. So I understood that we are standing before a very, very serious situation. And the next Shabbos, it was before Purim. Purim, it's a major holiday. People are mixing together. People are going to synagogues to hear the Megillah. Sometimes they're getting spread with tens of thousands of people in one synagogue in Israel, in the biggest places. And people from my family sending me notes and briefs from rabbis that claiming that in this Purim, it's still not a pikuach nefesh. We didn't order about outbreak. And of course, you have to go to Minyan. Even with the doctors told you that you have to be in a quarantine. They told me, if you are right, that we are standing before a very serious situation, so it's a major problem. You both people, the doctors and the community, are not speaking on the same channel. And I knew already in those days that we are dealing with a serious situation. We already got some data from Italy. Managers of the hospitals in Italy got connected with managers of the hospital by us and tried to schnorr ventilators and spreading, stories that they don't have enough and they have to decide people should be intubated or not. And I decided that I'm going to make my risk and going to speak with one of the biggest leaders, rabbis, that is very associated with medicine in halacha, rabbinical rules. And I made the appointment with him. I sat with him with my iPad. I showed him the graphs. I gave him a little lecture, you know, how pandemia is acting and what is the tools that we have now to stop it, that we don't have any medications or treatment. Right now, it just, you know, depends how the civilians and the community gonna act. And I told them, if we're not gonna take action now, we're gonna stand with thousands of dead people. So this is now the time to do it. He understood very quick what I told him, and he ordered one of his secretaries, big secretaries. It was in the middle of the night, and he told them, go make a phone call to the biggest newspaper of the Haredi people and tell them should not print the newspaper this night until I am giving you the note about new guidelines that everyone has to stick in with the guidelines of the professional people. He gave me a very, very strong note that it was also published in the first page, and I think it was very important in that time. I can tell you guys, the Americans, I believe a lot of you are Americans, that I tried in those days to get connected with a journalist of and rabbis and doctors from the Hasidic and ultra-Orthodox community in the United States, and to get them also, you know, to get their attention, they should try also that in the American community, people should not get mixed in big places, because I knew that the reason that the Americans didn't add in that time a lot of patients sick, it was not because they didn't add a lot of patients sick, they just didn't examine anyone. And that point when in Israel they made already 7,000 tests, how much people are have COVID-19. In the United States, they had in that point only 200 samples. So, but you know, probably until the managers and the politicians getting the call, no one gonna believe you. And indeed, people laughed at me. Later, we started getting a lot more patients. The stream became more and more intensive. I was also in Purim, you know, always in normal years, you can switch shifts with a friend that is not keeping Purim, that he doesn't need to be with his family. But in those days, you know, no one got a discount. So I spent Purim and almost any Shabbos, any Shabbat, Saturday in the hospital. It's very interesting also, you know, as doctors, I think we're a very traditional profession. You know, we know how to do it for hundreds of years, how to examine the patient, but because of this situation, because the disease is so contagious, so we got pushed, especially by us in Israel, to apply and to put a lot of devices that can release you from getting exposed to the disease. So like, let's say, even a stethoscope, I don't have to go inside and to expose myself to the patient that is contagious. We're just giving him when he's getting hospitalized, you're getting a kit with a electronic wireless stethoscope and good cameras, and we can examine them, you know, from far away. And we have very smart sensors. The more critical patients already in the admission, we're putting a special sticker with a little device like a matches box, you know, and is giving us the EKG 24/7 and the saturation, the cardiac output, and all different parameters and data that we can control them from far away and to see towards what the patient is coming. Right now in Israel, we are pretty much very, I think the people are very cooperable with the guidelines of the professions, the epidemiologists, and the numbers are pretty much stable. The bigger question is what is going to be in the upcoming 48 hours, you know, in Leila Seder. It's the Passover that traditionally all the families are getting mixed together. It does not matter if you are religious or not, but I think it's one of the biggest events in the Jewish calendar that everyone is getting us mixed together, families and events. And this is the biggest question: how much people going to be careful not to get mixed this year? That like this, maybe next year we can see our loved and our grandfathers and grandmothers and people in risk still alive and continue having normal lives. I think this is the major question right now.
Thank you very much. You know, like everyone on a Zoom call, there's a situation when you start speaking and you realize, oh, I'm still on mute, and that's what happened to me. Thank you very much, Dr. Sabiner. Thank you for your participation. I know that you're about to start your rounds. One question for you that I think is more of a personal nature, but I think it's also profound, and that is, you know, in strong Jewish communities, such as in the religiously observant ones, so much of what we celebrate together. And I'm just wondering, how is it that you, as an observant Jew, a family man, and as a medical practitioner who understands what's going on, how do you communicate to members of your community what is needed to be done right now so that it can resonate, and yet you know that it's not easy, it's painful?
So I maybe didn't mention it, but I'm living in Bnei Brak. Bnei Brak here in Israel right now, it's the biggest outbreak center. We have there sick people, dead people, and very critical ill people in bigger and higher percentage of the community of the Israeli population. It has a couple of reasons. One of them, it's because the high density that people live there. Sometimes you can have there 8 people in one house of a 50 meter square, 60 meter square. And also traditionally, you know, as a observant, you're going to daven in minyan a couple times a day for a long time. So it's hiring the risk to get infected and to get other people infected. But right now, I think in the last 2 weeks, people understood pretty well and very sadly what we're dealing with, because, you know, we have already sick people and very ill people all over. And I'm in the Shiva hospital. I had a conversation last week with the head of the Department of Infectious Diseases and the head of the Department of the Corona Department. And they asked me if I can stay in the hospital and not go back to Bnei Brak for the safety of me and for the safety of the staff. You know, we cannot have now staff getting out of the pool of employers. And together with my wife, I decided to stay in the hospital for the whole week. Yesterday, I passed the Corona test, and I was negative. And for tomorrow morning after the shift, I'm gonna go back to my house to Leila Seder. So pretty much, I don't think that right now it's a major, you know, concern if people going to stay at home in Bnei Brak, because in Bnei Brak it's very sad. They got this smack in the face, and they have people, you know, all over very ill. So I think people are scared, and they're going to keep the rules. but still we're trying, me and the rabbis and the leaders, everyone is sending the message that we have to do it, as also as a religious mission. It's a pikuach nefesh. And a pikuach nefesh, when someone is in risk, you allow to mechalel Shabbat. You don't have to keep Shabbat. You don't have to keep Yom Kippur, and you don't have to keep nothing if it's a situation of life or death. And this is the situation that we're staying now in this point. So I think the message is going through very good, and hopefully we're going to see after the holidays that the numbers are not rising up. Really hope so.
Dr. Sabiner, thank you so much for joining us. For those of you who are joining us from around the world, in Israel, it's about 7:21 right now. Many people are at home and enjoying the evening, or just participating in the evening. A few more hours of the day left to go, but for you, it's the start of your work shift, and I just really would like to thank you for being able to join us. We wish you Mazal Tov in your efforts, of course, a Chag Sameach, and may the work that you do on behalf of the people who you're serving continue to give them health, keep them alive, and help them so that we can, as we say, celebrate next year in Yerushalayim, that we actually can do that. And of course, you're a little closer to Jerusalem than most of us. So thank you for joining us, and your words and your insights really mean a lot to us. Toda Rabah.
Thank you. Chag Sameach.
Chag Sameach. So let us then go on to introduce our Technion researcher. I'd like to begin just with words from Technion Uri Sivan, who recently said that Technion's impact is that its interdisciplinary collaborations are able to generate rapid and sophisticated solutions to help the fight against COVID-19. And I truly believe that our next speaker can be truly considered as a symbol of that statement. So Assistant Professor Yaron Fuchs heads the Laboratory of Stem Cell Biology at the Technion, also focused on regenerative medicine, and is also a faculty member both of the Technion Integrated Cancer Center and the Lori Loquet Interdisciplinary Center for Life Sciences and Engineering. He holds the DeLauro Career Advancement Chair for Leaders in Science and Technology, and is also associated with our wonderful Russell Berry Nanotechnology Institute. While scientists have long studied cell rejuvenation, Technion alumnus Professor Fuchs really had the courage and insight to follow a very different direction and look at the flip side of stem cell renewal, in other words, cell death. He broke unexplored ground and is leading truly novel insights and strategies into tissue generation, including the very recovery processes that occur in parts of the body, such as intestines, hair growth, cancer treatments, and very excitingly, the potential regrowth for certain organs. So it's no surprise to hear that Professor Fuchs is being recognized for his research. In 2019, he became Israel's first scientist to win the prestigious American Association for the Advancement of Science Grand Prize for his groundbreaking work. Given the current global health crisis, Professor Fuchs is now leading his team in terms of research about how cell death can lead to better ways of containing viral infections and specifically combating diseases like the novel coronavirus, hopefully for new drug developments or other kinds of therapies. And according to him, it just might. Now, before I finally turn it over, let me just mention a couple of other things. Number one, we do have a Q&A feature. So use the feature at the bottom of your webinar window, and my wonderful colleague, Jerry Kleinman, will facilitate the Q&A after Professor Fuchs speaks. As well, the presentation is also being recorded, so a link can be sent to you in the next couple of days. So if you want to see it again, or more importantly, share it with someone else, you will have that opportunity to do so. So finally, I'm thrilled to introduce Professor Fuchs to discuss his life-changing work. Yaron, welcome.
David, thank you so much for the incredibly kind introduction. And everybody, it's an absolute pleasure to be here. It's great to be with you today and to have the platform to talk about my work. So I thought I'd give a bit of an intro. What is cell death? What is cell suicide? And how can we actually harness its incredible potential to heal better, to treat cancers, and also now in order to tackle this devastating disease, COVID-19. So I want to start by saying that every second, approximately 1 million cells in our body commits a form of cellular suicide known as apoptosis. So think about it. Every minute, we're talking about 60 million cells. And in an hour, we're talking about 3.6 billion cells. So we're talking about a vast number of cells that are deciding to kill themselves. Now, why would a cell go forward and decide to commit suicide? So within these cells, they have these mechanisms that enable them to examine what's going on. And if they have specific mutations that they're able to repair, great, they're going to repair it. But in the event that these repair mechanisms are not actually functioning, then the cell understands that it actually has to kill itself in order to protect the tissue and the organism. So we're talking about 1 million cells per second. And this is what happens during adult organisms in our adult lifespan. But actually the function of cell suicide starts all the way back during embryonic development. I'll just give a few different examples. So if we look at our fingers, right, during embryogenesis, we have webs connecting our fingers. And waves of cell suicide just eliminate these webs, these interdigital webs, individualizing our fingers. Same idea was what happens in the heart. If we look at oocytes, vast number of oocytes are produced, but more than 50, 60% are actually eliminated. So a lot of cells are actually killed in this process. If we look at our immune system, during embryogenesis, cells that can attack the self or that are not potent are eliminated. And in other examples, such as during metamorphosis, think about metamorphosis, for example, the entire structure of an organism changed, and it's sculpted by cell suicide. So I was very intrigued by this process of cellular suicide, and there are a few different forms of cellular suicide. I'm going to talk about specifically one form known as apoptosis. In Greek, it's shedding of leaves. And I was intrigued in the sense of how could that be linked to stem cells? So just a few words regarding what are stem cells. So the first stem cell, if you have an egg, the egg is going to be fertilized by a sperm, right? That's going to give rise to the first cell. And that cell has the capacity, the potential, to give rise to each and every organ within our body. So it can give rise to the ears, to the eyes, to the heart, intestines, and so on and so forth. So from just one cell, it has all that potential. Now, this cell goes over and starts dividing, and each cell goes over and starts taking a specific fate. Now, these stem cells are characterized by two traits. One, they have the capacity to give rise to more and more stem cells. It's called self-renewal. And two, they can differentiate, they can generate different types of cells. For example, cells of the eye or of the tongue, and so on. Choose your favorite organ. Now, due to the fact that stem cells have been characterized by self-renewal and differentiation, most studies in the world have actually focused on these two processes and how stem cells are actually performing these incredible feats. But I was intrigued by something else. I thought about it and I said, well, a stem cell can do all that. And if we think about stem cells within our body, stem cells of the skin, of the hair, of the intestine, of the blood system, these stem cells are there for very long periods of time. And during that time, they're subjected to all these insults. Now, you never run out of skin. You still have skin even if you're 120 years old. So you have to have these stem cells at the base replenishing and fueling your different tissues. So how do these stem cells cope with that stress? And do these stem cells die? Because for many years, they were considered to be these immortal cells. So we started examining that, and we found that cell suicide is a critical mechanism which actually regulates stem cell biology and stem cell dependent processes. And stem cells are critical in repair and healing and growing of different organs. And also the flip side is what happens during tumorigenesis of cancer generation. So the first thing that we started doing was to understand the process of specific proteins. And you can think of these proteins kind of like sprockets in a machine, right? So you have this bomb that's supposed to detonate in order to kill the cell, for the cell to explode. It has to be very regulated because you don't want the cell to die without proper instruction. But what are these machineries? How do they actually work? How do these sprockets turn one another? And during my postdoctoral fellowship at Rockefeller University at the laboratory of Professor Herman Steller, I found, or we found, it's a lot more precise to say, is that what we found is that there are specific genes or specific proteins that are expressed within these stem cells, and they're critical for stem cell death. And if you take away, if you just erase, if you delete one of those genes, a gene known as CEP4-ARTS, that was discovered by Professor Sarit Larish at Haifa University. So if you delete this gene, you actually find that you get this vast expansion in the number of stem cells. So we said, okay, we have a lot more stem cells. What actually happens? Why do we have more? And we found that indeed it is because these stem cells are not undergoing cellular suicide, not undergoing apoptosis. So we then thought, okay, if we have an animal with more stem cell, are these mice going to heal better? Are they going to regenerate better? The difference between healing and regeneration is if you have ever inflicted a wound or if you look at the different wounds that you had, you'll be able to see it because you have a scar. And a scar is an indication that you had a wound there. You still have a functional tissue now, but it doesn't go back to the way it was before. So that's wound healing. Regeneration, you're not going to be able to detect. If you look at salamanders, you can amputate a salamander, it's going to grow its entire limb back. So that's regeneration. So I started thinking perhaps these stem cells are going to enable the animal to heal and regenerate a lot better. So we inflicted wounds on the back of mice, and what we found is that these wounds heal significantly faster. We're talking about at least 10 times faster. But the most striking aspect was when we actually zoomed in on these wounds, and we found that from within the wound bed, from within the wound, we have regeneration of hair follicles. And hair follicles that give rise to hair normally form during embryonic development. They're not supposed to form during the adult lifespan. So that was fascinating. It generated a lot of buzz. And what we find now is that we can actually harvest specific stem cells, hair follicle stem cells. We can combine them with other populations of skin cells, and we can actually graft them and generate a tremendous amount of hair follicles, so regeneration of hair follicles. So based on that, now we're also designing drugs to be able to specifically target these proteins and to be able to drive faster healing, faster repair, and potentially hair regrowth. So that's one of the things that we're definitely focusing on. Now, while we're working on this, and feel free to stop me with a question. I mean, it's completely okay with me if you want to throw questions my way and I'll just answer midstream, or if you want me to wait until the end and then take the questions, whatever you guys.
We'll probably wait till the end, but okay. Please, everyone, keep feeding your questions to our Q&A. As you can see, Professor Fuchs wants your questions and we'll deliver them.
Yeah, all right. So while we're working on this, we're actually intrigued with if you have a cell committing suicide, right? What is the effect on the neighboring cell? What is the eulogy, if you will, of a dying cell or a dying stem cell? And what we found is that stem cells send out signals when they're undergoing apoptosis. So this process was first found in flies and Drosophila at the laboratory of Herman Steller and Hines Murata. And what they found is that when cells decide to die, they send out these signals instructing neighboring cells saying, listen, I'm dying, please divide, please proliferate and take my place. And it's called compensatory proliferation. So we started working on that, and we started understanding that there are various signals that are actually released from an apoptotic cell. And what we found now is that really by unleashing this power by trying to understand which factors are released and what is the function of these released factors. We found that we can also heal a lot faster in different organs. So we can repair the intestine in situations of inflammatory bowel disease or Crohn's disease, wound healing of the skin, various regenerative paradigms that we're examining. We can actually see that specifically by targeting the signals that are released, either blocking them or inducing them, we can actually drive regeneration in a lot better sense. And if you think about it, it's great in a form of regeneration, but it's actually critical to what happens during cancer. Because many of the ways in which we kill a cancer cell, we're trying to induce cell death. We're trying to induce apoptosis. Think about it for a sec. The classical therapies for treating cancers would be either chemotherapy or radiation. And I remember when I was a kid, my mom always used to tell me, if you go to the beach, you have to take sunscreen because all the radiation is going to give rise to cancer, right? So now you got cancer, but you're bombarded with radiation. And the reason for that is because we want radiation to induce mutations within your DNA in order for the cell to say, all right, I can't fix this. It's unrepairable. I'm going to have to kill myself. So that's why a cancer cell actually decides to die. And it decides to die. It's not as if we're killing it. We're not murdering the cell. We're just telling him, all right, the gun that you have within you, please use it on yourself and commit suicide. Now, I just told you that these dying cells can release factors, and these factors can drive proliferation of surrounding cells. So wait a second, we're not doing something right, because we're trying to drive cell suicide within the tumors, and it works nicely in many occasions. But in many occasions, actually, we have secondary tumors, we have relapse, we have metastasis. So we start understanding or start examining whether these functions could actually be targeted in order to generate novel therapeutics for different tumors. And we start examining very difficult to treat melanoma, stage 3, stage 4, in which pretty much whatever you throw at them, it doesn't really make a difference for the tumor. And what we found is that by targeting these specific components within the cell death machinery and these signals which are released, we could actually have dramatic effect on cells that, or on tumor cells or tumors themselves that normally are considered to be untreatable. Right? So we've patented this technology, and now we want to take this forward. We want to take both the regeneration to be able to heal a lot better, to generate hair follicles, and also to be able to design and develop new therapeutics for tumors. Now, one of the beautiful things that you can do with stem cells in the lab is if you know how to isolate them and give them the proper cues, you can actually generate these organs within the dish. And it's beautiful because you can just take them out, right? There's specific ways to actually isolate these stem cells. You put them in the dish, you give them the proper factors, proper medium, and they start assembling into the tissues, start assembling into the organs. So what we've recently been able to do, we've been able to generate sebaceous gland organoids. And sebaceous gland is an organ which sits on the side of the hair follicle. The hair follicle looks pretty much like this, I would say, and then the hair just pops out of the skin. And on the side of the hair follicle, you have these glands called sebaceous glands. And sebaceous glands secrete sebum, the oily substance, making both our hair and our skin oily. In the event that it becomes clogged, for example, in the event that they're subjected to a lot of hormones, for example, during puberty, they start growing in size, they become clogged, and it's an ideal place, an ideal niche for a specific type of bacteria known as P. acnes to start dwelling there, and that gives rise to acne, to a zit. So we started thinking maybe we can actually isolate these cells, the stem cells of the sebaceous gland, and to give them the proper cues, because there's no ideal therapy or ideal drug for acne, for alopecia vulgaris. And we've been able to do so. We've been able to isolate these stem cells, give them the proper instructions, and they really generate a sebaceous gland within the dish. So being able to do so, we said, all right, perhaps we can actually also recapitulate the different aspects of acne and use it as a system that we can actually find new drugs in order to treat acne. So we found conditions that we could really grow zits, if you will, acne within the plate itself. And we could find new drug targets and potentially new drugs in order to treat acne vulgaris. So that's another thing that we're working on right now. And again, we find that by targeting apoptosis within specific compartments of the sebaceous gland or of different organs, we can actually design drugs in a better fashion and hopefully heal both wounds and from different tumors. So that's kind of a big overview of the kind of work that we're doing presently. Now, an interesting aspect regarding cell death and infection of viruses is the fact that you can consider cell death as a defense mechanism. You have the virus, goes over into the cell, infects the cell senses what is going on. And if it decides to undergo cell suicide, in the same way that same idea of a mechanism that is able to defend the cell or defend the host, right? If the cell decides to die, it takes the virus away with them. And one of the things that we found alongside with Dr. Ainhoa Perez-Garijo and Professor Herman Steller is the fact that when cells are dying, they also secrete factors killing neighboring cells. So a cell senses that it's been infected, senses that it has to die, and as a result, it's signaling to its neighboring cells, listen, I've been infected. If we generate this perimeter around us, right, we're going to be able to block the infection in this sense. Now, viruses, different viruses, and also viruses within the corona family, they're very tricky, right? So on one hand, they are trying to block apoptosis or block cell suicide in the beginning when they infect. They have different mechanisms enabling them to do so. In other aspects, what they're actually doing, they're trying to generate the cells to die after they actually generate a large number of viruses to be able to release in a better kind of a form. So we're trying to understand these functions, and we're trying to see whether we can actually block specific targets in order to attenuate or to inhibit the propagation of viruses, different viruses. So that's kind of an overview of the work that we're doing right now.
Thank you very much. And I'm about to turn it over to my colleague, Jerry Kleinman. One question that has come up from your wonderful presentation is, I think many people are concerned, and this was reflected in the questioning, about even those who are able to overcome COVID-19, but had a very bad bout with it, and there may be damage to the lung tissue.
Yeah.
Does any of your research suggest treatments for damaged parts of the respiratory tissue?
So it's definitely things that we're considering, that we want to examine. I would say that the strategies that we've been developing during the past few years in various organs that we examine, and we're just starting to examine the lungs right now, right, using specific models for what's going to go on with the lungs. I think it's a beautiful question. I completely agree. But in all the different organs that we examine, we could see that we can tap in to these programs and we can drive faster repair and healing. But it has to be done in a specific point of time. Okay? So if the damage has been done and we come over and we try to treat it, it's not going to be as ideal as if you catch it specifically once the damage is actually occurring. Okay? So you have the therapeutic windows in which you actually have to conduct, right, or to administer your drugs. But if you do catch it within that time frame, then we see, dramatic effects, right? Whether we're talking about skin and incisions or excision wounds, whether we're talking about different modes within the intestine, also within the eye. So we're just starting to examine the lungs right now, obviously because there is a critical aspect to it, but we still don't know. But I would say I'm optimistic in a sense that what we see right now is that in the different tissues that we examine, it works in the same kind of way.
Interesting. Thank you. I'm going to turn it now to my wonderful colleague, Jerry Kleinman. He's our Executive Director for Principal Gifts at the American Technion Society. And Jerry, take it away.
We can't hear you. You're muted.
Right. I did the same thing. Sorry about that. Thank you, David. Thank you, Professor. So I have to ask, because several people on the who are participating know that most of the labs at the Technion have been closed.
Yeah.
And,
Yeah.
and in fact, notices have gone out both from the American Technion Society and the Technion itself that there are 20 or 25 labs which are open, which are dealing with COVID-related areas. Is your lab open and running, and what are the challenges in doing that?
So all labs, so I would say this, my lab has been closed for a few weeks now, right? And we just got the green light. So sets of labs, right, got some green lights, whether they can go back to work. Specifically, it's related to COVID-19 or designing, various ways for diagnostics, right? Or potentially drugs. It's going to take time, obviously, in order to be able to generate it. But yes, so just today we got the green light, right? Which is fantastic. It's not going to be at maximal output. So right now they just allow 2 students to go back to work in the lab, just 2, right? And that way they're going to be able to work within the same lab, but they're going to be working at, distances between the 2.
And yourself. And yourself.
And I can, yeah, and I can go. Yeah. And myself, I'm going to be within the office. Yeah, that's pretty much the way it's going on right now. I will say that I'm kind of optimistic in a sense that hopefully, right? Hopefully, after Passover, we're talking about the 19th of April, there is a sense, right? There's an optimistic wind, which is blowing that, the labs are going to be, more labs are going to be allowed to open up. And the labs that are open right now are going to be allowed to actually, increase the number of students within the lab. Yeah, that's what it appears to be. But obviously the administration and the Technion, they're very cautious because it appears that although it's somewhat contained right now due to the fact that, some wise steps were taken initially, still the country's on lockdown, right? So in effect, they're afraid, and rightfully so, that in the event that just people go back to their works, we're going to have a second, strong wave. Yeah.
Interesting. And for several of the people that wanted to know how the labs stay open, and to use a phrase I think that I'll steal from Governor Cuomo, is the valve of funding from Europe and elsewhere tightened up? Is it difficult to keep these labs open and going?
Yeah, it's difficult. I would say that we're entering a new era in that sense.
Yeah.
I would say that being able to raise the funds required in order to run labs in which the experiments that you're actually doing are expensive. Definitely, I can talk about my lab. So doing either stem cell experiments, which cost an obscene amount, and also doing animal research that you have to have in order to generate drugs, I would say it's very, very pricey. And seeing how the economy worldwide, right, the direction that it's taking right now, I would say that there's going to be some, rough water ahead of us. That's what I think.
I think that's why the planning has gone forward with a couple emergency funds, one on the student needs end and one on the research end. And anyone who wants to know more information about it can chat, send a question and answer, and we'll provide information separately on if you want to know more. An interesting question that came in. Are you, someone asked if you were associated with the Hershko and Chiconover labs, who deal with cell death. Just curiosity from one of our board members, actually.
Yeah, so Hershko and Chiconover, right, the Nobel laureates within the Technion, were awarded the Nobel Prize for their finding in protein degradation. So what they try to understand in their research is how are proteins actually regulated. So a lot of research in the world has been focused on how genes make proteins and what the function of these proteins, but their beautiful discovery was the fact that they could find a mechanism that actually tags proteins for destruction. So they're not working on cell death and you know, how cells decide to eliminate themselves, but they're working on processes in which how proteins are dying, if you will, or how proteins are sent to degradation by a big complex of protein known as the proteasome. That's pretty much their beautiful discovery.
So I've got some technical ones, and I'll try to do justice. What is the role of the mitochondria in the apoptosis and the regeneration process?
All right. So the mitochondria is the powerhouse of the cell. Okay. Think about it. You have these power plants within the cell, and they're supplying the energy for the cell. Now, what's interesting is that within the mitochondria, or on the outer leaflet of the mitochondria, has a membrane around it. So you have proteins within the mitochondria, and you also have proteins on the membrane surrounding the mitochondria. And the mitochondria plays a critical role in apoptosis, a really critical role. Apoptosis can be broken down into two sorts. I'm going a bit technical, okay? It can be broken down into two sorts. We have what's called extrinsic apoptosis, and we have intrinsic apoptosis. Extrinsic indicates that if we have a cell, on the outer membrane of the cell, there's a receptor that binds to a ligand, and that starts a domino effect, right? That tells the cells to die, to undergo apoptosis. But the signal comes from outside, okay? That's called extrinsic apoptosis. Intrinsic apoptosis is, in a sense, for example, that you have these mutations within the DNA. And in that sense, the cell checks itself out and is saying, I should kill myself right now. And in order to do so, it actually taps into the mitochondria. And what happens is that within the mitochondria, you start having these pores, and these pores start releasing factors. And the factors that are released from the pores are critical in driving apoptosis. So these factors are responsible for generating multi-protein structures. One of them is called the apoptosome, right? And it's responsible for activating these processes or activating these proteins. And one of the proteins that it activates, or one family of protein that it activates, is known as the caspase family. And the caspase family, or a specific caspase member, goes over to the apoptosome, becomes activated. And you can think about it like a samurai that just goes around the cell and just chops vital proteins, right? And what it does,
so let me ask you a question to tie into someone else's. I didn't mean to cut you off, but how can we use cell suicide to advance healing?
Okay, so the question is, once we actually, so a lot of the experiments that we're doing are by using mice in which we completely delete the gene. So if you don't have the gene, you don't have the protein. So that we understand what happens if we delete a gene. And you can think about it, when we generate a drug, now by that we'll be able to say, okay, I deleted that gene. Now I can see that the mice healed a lot faster. What happens now if I generate a drug, a molecule that is able to bind to the protein that is derived from that gene? It's very similar to deleting that gene. So if I make that molecule, it binds to that protein, this protein is not going to be able to work. And when it's not able to work, for example, I can see that the animal is healing a lot faster, right? 10 times faster, regenerating hair, and so on. So by performing these experiments, and then by following up and finding specific drugs that bind to these targets, in that way I can actually harness their potential for better repair and healing.
So as we get near the end here, we have several questions. What has your journey been that brought you to the Technion? What has been the journey personally and professionally that finds you here right now?
I love the Technion. I love it, right? So I did a direct Ph.D. track at the Technion, right? And after I performed,
before that, before that,
all right, before that, so I'll take it from the top. So I was born in Israel, right? Born in Israel. My dad's a rocket scientist.
That makes it easy for you, right?
Yeah, I guess so. So from here, we moved over to the States. Then we came back to Israel. Then we went back to the States, back to Israel. So we ping-ponged between the two and used to work with the United States Air Force. Then finished my high school here, got drafted, and afterwards went over, became a diving instructor, if we want to get into the specifics. Was mesmerized by the coral reef, by the ocean, and decided that what I want to do was to be a marine veterinarian, a marine vet. That's what I thought I wanted to be. And in Israel, in order to be a vet, you actually have to study either biology or agriculture. And I said, well, agriculture is not really my thing. I'll go for biology. And during my undergrad, I started working at a vet's office. And I found it to be somewhat, just from my perspective, somewhat dull, right? I liked the surgeries and so on, but I just felt as if it wasn't insanely challenging for my aspect. But every course that I took during my undergrad, I was just blown away. So I took genetics. I thought I wanted to be a geneticist. I took embryology. I thought I wasn't the embryologist. In the end, one thing that really caught me was genetics, and I combined it with my love to the sea. And then I started working at Israel's Oceanographic Center, right? And I started performing experiments on soft corals and understanding their biology. But then at some point, I thought it's not enough. I want something else. And then I got a tip from a friend who worked there that there's a great professor at the Technion, Professor Yaron, in the biology department. And I remember him saying, he said, listen, if you go there, she'll make a scientist out of you. And it hit home, and I went there and I performed my direct track there. And then when I finished my PhD, I moved over to New York, to Rockefeller University. It's considered kind of like the Mecca of biology. It has 24 Nobel laureates and so on. And I went to the lab of Professor Herman Steller, a pioneer in the field of apoptosis, of programmed cell death. And he was incredibly generous, let me work on what I was fascinated with, programmed cell death in stem cells. And then after the end of my postdoc, I had the ability to either stay in the States in good places or to go to really terrific places in Israel but I definitely wanted to go back to the Technion. I love the place, you know? So I wanted to go back here. Yeah.
David, do we have time for one more or no?
David, we can't hear you.
I know. I was just the same protocol as before. Couldn't find my unmute button. I think the last question, I'll pose it. And some people, Professor Fuchs, have been wondering about the cockroaches in the back of your room. Just to let you know, we lost 30 participants because they got grossed out. Just kidding. Wanted to know. A couple people asked about that.
So I'll give you. All right. So I just found these. I'll be honest with you. I just walked around IKEA and I saw these two really beautiful insects, and I said, "Wow, they're going to be gorgeous on my wall." That's pretty much it, right? That's what I can tell you about these guys. That's the truth, you know.
You know, different people have different bedroom decor. Now we know of yours. We really wanted to thank you for your time. Just to reiterate for the people who are still with us, and that is, you know, you're joining among 32 labs at the Technion that are working round the clock right now, trying to move things from the lab bench to bedside, together with our partners at Rambam Hospital and elsewhere. We thank you for that. And look, we know this is one heck of a time to be talking about philanthropy, but for those who may be interested in participating in a way that they are able to in COVID-19 research that's real-time and applied and can make a difference to saving lives, the Technion offers you, like other universities, an option, but I myself would place a big bet on Technion. So I just want to thank you, Yaron, for being here, and for all those who joined the call. Thank you for being here. If you commemorate Passover, I wish you Chag Sameach, and wherever you are around the world, please stay safe, stay healthy, stay connected to those who are important to your world, and stay sane. And we look forward to seeing you again. All our very best. And again, thank you, Yaron. It was really a pleasure to see you.
Thank you so much, David. Thank you, Jerry.
All right.
All right.
The heat throat, as they say. The heat throat. Bye-bye.
Bye, Nicolás.
Okay. Bye for now.